Hello, Chem 2. Welcome to the second edition of the acid-base equilibrium series. Today we're going to focus on what the heck the pH scale is and why is it there and how are we going to use it. The last video of the series, we're going to focus a lot more on bringing equilibrium back and all that we can do with these cool equilibria. So far in the last video, we focused on the concept of the Bronsted acid-base model and what makes something an acid or base, and more specifically, how do acids and bases act. Today, we're going to focus on section 2 and section 3, and notice something really cool about water, which you should be somewhat aware of because you may have seen it coming from the last video, and then we're going to address the pH scale and this other scale called the pOH scale. So let's first talk about the ionization of water. In the last video, we talked about water being amphoteric and the fact that it can act like an acid or act like a base. Well, here's the reality check. When water, pure water, absolutely pure water, nothing else is in there, zero is engaged, you're going to have a reaction where one water is going to donate a proton to the other water. And one of the waters is going to act like an acid, and one of the waters is going to act like a base. And the reality is that it's going to do that on a very small scale, but in an equilibrium that is going to happen. You're going to have the water molecules colliding and hydrogens going back and forth between the two. Water ionizes. Now, with that being said, this is an equilibrium. So with an equilibrium, we have an equilibrium constant. Okay? With an equilibrium, we have an equilibrium constant. So if we have our equilibrium constant here, the KEQ, we have hydronium times hydroxide divided by 1 because both the waters are liquids in their original form. So this K is a constant. We give it its own value. We give it its own variable, much like we did our Ka for acids and Kb for bases. Now we have Kw for water. And Kw for water, most specifically at 4 degrees Celsius, but it's what we're going to use exclusively, is 1.0 times 10 to the negative 14th. That's small. That's a really small KEQ value. This reaction lies very minimally towards the right, but here's where the fun part is. Hydroniums and hydroxides are always going to be present in any aqueous solution. And there's always going to be some quantity of hydroniums and hydroxides in that aqueous solution. So, because of course it's equilibrium, everything has to be present. So as one goes up, the other one has to go down. As the hydroniums increase in concentration, the hydroxides have to go down. But I'm going to say it one more time. We do not get to the point where there is zero of either one. So we can use that a little later on. So we have this new equation. Hydronium times hydroxides equals 1.0 times 10 to the negative 14th. Okay, so that is the ion product of water. Now, if we do a little bit of weird math, we realize that in pure water, if hydronium and hydroxide are the same, hydronium and hydroxide are the same, then the concentration of hydronium and hydroxide is going to be 1.0 times 10 to the negative 7th. That's a really tiny amount. Let's write that down. Ready? Let's see if we can make my pen work. There we go. 0.1234561 molar. That's not much. That's a very tiny amount in pure water. Very small amount. So in neutral water, the hydronium, or the hydrogens, and the hydroxides are equal, and they're at 1.0 times 10 to the negative 7th molar. In an acidic solution, the acidy molecules, the hydroniums or the hydrogen ions, are going to be greater. And in a basic solution, then the hydroxides are going to be greater. So we look at acidic and basic as being a balance between the concentrations of the hydroniums or hydrogens and the hydroxides. When they are equal, it's neutral. When there's more hydroniums or hydrogens, it is acidic. And when there are more hydroxides, it's going to be basic. So you have this proportionality, but again, you're always going to have a combination of hydronium times hydroxide is going to be 1.0 times 10 to the negative 14th because it's in equilibrium. So let's move on to this pH scale. So in Chem 1 and in middle school, you talked about the pH scale. And you talked about what the heck the pH scale was. And some of the things you learned about the pH scale back in Chem 1 was it's used to measure the acidity, that is usually in the range of 1 to 14. Your teacher probably told you, as I did a little bit ago, that you're going to, and even back in middle school, he says 7 is neutral. And then pH little numbers is acidic, pH big numbers is basic. At which point, probably back in the middle school days especially, you probably ask yourself, why 7? Why did they pick 7? If this cool scale is going to give you an indication of whether something's acidic or basic, why in the world would they pick 7 as the middle? I don't think any scale I've ever used uses the number 7 as the middle. Maybe the number 5, maybe the number 10, maybe the number 2, maybe the number 1, but not 7. That's a weird number. We've seen it already. Let's take a trip back. What's the concentration of hydronium at a neutral solution? 1.0 times 10 to the negative 7th. There's my 7. That's the 7 that's associated with the pH scale. So what we have here is the fact that pH is a way to express the concentration of a solution. More specifically, the concentration of the hydrogen or hydronium ions in the solution. So pH actually stands for the power of the hydrogen ion. So if I want to know the concentration of a solution, concentration of hydronium or hydrogen in a solution, it's 10 to the negative pH. So our previous example of neutral water, the pH was 7, so 10 to the negative 7th was the concentration of the hydronium ion. Vice versa, something you may have had some contact with is this logarithm scale. We talked about the logarithms in a previous one. This time we're using not the ln, the natural log, we're going to use the log base 10. I know it makes things a little weird, but this one's actually the more common, at least in science, used logarithm. If we're going to reverse the operation of an exponent, remember that was the logarithm. So we have two equations here. We have pH is the negative log of the hydrogen, or the hydrogen ion is 10 to the negative pH. So if we have one, we can get the other. If we have one, we can get the other. And better yet, we don't have to have pHs that are whole numbers. We can use decimals. We can do 10 to the negative 2.7, and we can go ahead and calculate that number. So the higher the pH, the less acidic. Think about it. If this number, this pH, was 10 compared to 7, 10 to the negative 7th compared to 10 to negative 10th, which number is bigger? Well, the one with the smaller pH. So it's going to have as the number goes up, the concentration is going to go down. Hence the reason why big numbers on the pH scale are the basic solutions and small numbers on the pH scale are the acidic solutions. You could also use the same concept with pOH, and it's not really used that often, but there is a convenience factor associated with using pOH, and that is the fact that if you don't want to go through that 1.0 times 10 to the negative 14th conversion, we have a comparison that if we just do the exact same math, but instead of talking about the hydrogen ions, we talked about the hydroxide ions, then what we're going to have is a pOH scale. Same logic. pOH is negative log of the OH, and more specifically, I'll write over here because I didn't put it on here, that the hydroxide concentration is going to be 10 to the negative pOH. Okay, so using the pOH scale just gives you an opportunity to determine the concentration of hydroxide or to go back and forth. And I'm not going to bore you with the logarithm math, but whatever the pH of a solution plus whatever the pOH of a solution, that's going to equal 14. Here's that 14 again from the 10 to the negative 14th. So what we have here is a series of equations, and these 6 equations we're going to use like crazy in the rest of this chapter. Okay, where we're given amounts of hydronium or hydroxides, or given a pH. And actually, one of the cool things about this chapter is I had said that in the previous chapter we have pressures and we have concentrations, and that's what equilibrium is all about. And we're comparing the changes in equilibrium, acids and bases, and changing all that stuff. I just fumbled through my words really, really bad. Sorry. We're going to offer the differences in the concentrations. But here, a way to give a concentration, a way to give the concentration of a solution, especially revolving around hydronium or hydroxide, is to use the pOH scale or the pH scale. And that's what's going to happen here. They're going to give you a pH, and that's going to be a way for you to get to the concentration of hydronium. Or they're going to go through a bunch of rigmarole, and they're going to at the end ask you what's the pH, which means you're going to do one more step past getting the concentration. But everything in equilibrium round is exactly what we did in the last chapter, and that's kind of cool. So they talk about the different relationships as pH goes up, okay? As pH goes up, it's going to become more basic. As pH goes down, it's going to become more acidic, and they show you why using the numbers. So some different common materials and their pHs, you'll notice, like for instance, human blood is a little basic. Vinegar, of course, is an acid, acetic acid. Urine's a little, it can vary based on your water content. That's way too much information, but they just show you some common materials and their pHs. Okay, so let's look at an example of how we can use this. So consider the following solutions at 25 degrees Celsius. First question, find the hydrogen ion concentration and the pH of tap water. If the tap water's concentration of hydroxide is 2.0 times 10 to the negative 7th. So we take our information as given to us. We're going to do a strategy. Our strategy is we're going to use the Kw, get the hydrogen ion, and then we're going to use the hydrogen ion to get the pH. They gave us a hydroxide. We're going to use that first equation to get the hydrogen ion, and then we're going to use the pH equation to get the hydroxide ion. The pH. So there's my equation list. We're going to use the first equation first, and then we'll use the green equation second. So hydrogen ion, Kw is equal to 1.0 times 10 to the negative 14th. So we need to divide both sides by 2 times 10 to the negative 7th. And we find that the hydrogen ion concentration is 5 times 10 to the negative 8th. Question before we go any further, is that an acidic solution or a basic solution? Here's the way we know. Before we worry about the pH, okay? Which one of these two numbers is bigger? Is it the hydrogen concentration? Sorry, is it the hydroxide concentration or the hydrogen concentration? Which one's bigger? The hydroxide is, so hopefully it turns out to be a basic pH. Okay, so put the pH scale in, take that 5 times 10 to the negative 8, put it in, punch it through the calculator, and we get, bing, 7.30. That is just very, very slightly basic. It is higher than 7, so it's basic. Question number 2, find the hydrogen and hydroxide concentration of human blood at 7.4. So we have our information. We're going to use that pH equation again, and we're going to do it backwards. We're going to find out what the concentration is of the hydrogen. We're going to find out what the hydrogen ion concentration is, and then we're going to go backwards, and we're going to use that first equation again. So this time we're going to use the third equation. Since we have the pH, we can use this equation and go to hydrogen ion concentration. And then once we have the hydrogen ion concentration, we can figure out what the hydroxide is. So let's do that. So first part is we're going to use the pH. 10 to the negative 7.40 is my hydrogen ion concentration. I put that in the calculator. I get 4.0 times 10 to the negative 8th. Okay. Then I need to know the hydroxide. So I'm going to use that equation of the Kw and divide both sides by 4 times 10 to the negative 8th, and I get the hydroxide concentration to be 2.5 times 10 to the negative 7. You need to get used to using those 6 equations in all of their glory in all of their possible combinations. Here's one with a little bit of algebra. What is the pOH of a solution in which the hydrogen concentration is 5 times the hydroxide concentration? First off, is this going to be an acidic or basic solution? It's going to be acidic because our hydrogen ion concentration is 5 times the hydroxide, therefore it's going to be greater than the hydroxide. So what we're going to do is use our equation, but use it algebraically to find out what the hydroxide concentration is, and then use the pH equation to figure out what the pOH is. So we're going to use the first equation algebraically to find out what the hydroxide concentration is going to be, and then we're going to use this purple equation, pOH equals negative log of the hydroxide, to figure out the pOH. So let's do it. Hydroxide ion concentration. Since the hydrogen ion concentration is 5 times the hydroxide, I'm going to replace 5 times the hydroxide into my equation for hydrogen. So 5 times the hydroxide ion concentration squared is going to be equal to 1.0 times 10 to the negative 14th. Solve for the hydroxide by dividing by 5 and then taking the square root of both sides. I get that my hydroxide concentration is 4.5 times 10 to the negative 8. Now, I'm going to then figure out the pOH. So for the pOH, I just need to plug it into the equation, use my calculator properly, negative log of that 4.5 times 10 to the negative 8, get a number, and it's 7.35. That is my pOH. So let's talk a little bit about, before we dive into equilibrium with the next 2 sections, let's talk about strong acids and strong bases. In the last video, I gave you the list of strong acids and strong bases and talked about how they 100% ionize in water. That means there's no equilibrium, but that does not mean that there's not going to be the hydronium and hydroxide concentration. Once the acid, in this case the 0.1 molar acid, is dissolved in water, it is going to make 0.1 molar of hydrogen and 0.1 molar of chloride. So that solution, when you dissolve a strong acid into water, the concentration of the hydronium is going to be the same as the concentration you started off with acid. That's not going to be the case with weak acids, and that's what we're going to reserve for the next video. So you have the transfer over, strong acid, but 100%. All the hydrogens leave the hydrogen chloride to attach themselves to the water to become so the equal numbers of hydroniums compared to what the hydrochloric acid you started with. And the strong bases do the same thing. Okay, we talked about strong acids and strong bases, 100% dissociation. So whatever the concentration is of the base, it's going to be the concentration of the hydroxides, with the exception of the bottom ones, because those are going to be twice as concentrated since we have 2 hydroxides for every base. And that's it for this video, guys. Hopefully you got something out of this. If you did, go ahead and like the video, leave a comment, school appropriate comment. I look forward to seeing you guys on the next video. Everybody stay healthy, stay safe, practice that social distancing, and I will see you on the next one. Sig figs matter. Toodles.